Okay, here's the question. We want to use both the heliocentric and the geocentric system to explain a basic question. Why do we have eclipses? So we want to look at it in both ways. And let's start with the geocentric explanation, and let's look at that first. And here's the kind of drawing we've been working on for all semester. We're looking at the planetarium view of the sky, the geocentric view of the sky. North is over here, just to remind you. South is over here. East would be out here, and so on. West would be inside. Okay. I've drawn the celestial equator in blue on here. That's this line right in here. And the ecliptic is shown as the green line. Angle is 23.5 degrees with respect to the celestial equator. And let's imagine that we're going to look at a time when we actually don't see an eclipse. And we're going to look at the sun is going to occupy this position. I've arbitrarily chosen it to be right there. There's a sun. Okay? And of course the sun has to move on the ecliptic. It doesn't go anywhere else. So it's got to be there. There's the sun. And let's just say we're going to be looking at a solar eclipse. We're going to be asking about that question. And suppose I just happen to pick a time of the year when we don't have an eclipse. The new moon comes around. It does not block the sun. Why is that? Well, we understand it pretty well because the moon's orbit is not the same as the orbit of the Earth. It's on it's tipped by about 5 degrees. So let me sketch the plane of the moon's orbit on here. This is meant to be 5 degrees off of the ecliptic. So there it is, and let's just say I picked the crossing point right there. So down here, and now it's going to come up here and so on. Okay, so if we're looking at this is a 5-degree angle right there. That's 5 degrees. This is the plane of the moon's orbit. That's what we're seeing here with this red. Okay, and so if it's new moon, and you might think we'd have an eclipse. In fact, the way I've drawn it, the moon, which is right here, would be right close to the sun, but below it. Okay, moon moving faster is going to continue along toward the east along its orbit. It's going to be traveling along like that, in that direction, and the sun will be traveling like this. And when are they ever going to cross at new moon? They're going to cross when they're at this crossing point. So approximately 3 months after I've drawn it here, the sun will get to that position. The moon will occupy the exact same place in one of its loops around on its path, and we'll have an eclipse. So an eclipse is possible at new moon, and this is a solar eclipse, and it's possible right there. Okay, so 3 months after I drew it up here, and so we understand why it is that an eclipse does not occur every new moon, and we understand it from this this geocentric drawing. It's pretty straightforward. Let's look at it now from the heliocentric system. A little more complicated. So let's take a look at that, and let's imagine that we're going to be looking at the sun is over here, way over here somewhere. That's going to be the sun. We've got the Earth going around the sun, and this is going to be the moon's orbit around the Earth. So here's going to be the Earth right there. Okay, and moon is moving around, and we might be looking at it right here, but the moon gets to the new phase, and we don't see an eclipse at this position. Why is that? Well, we understand that because in the heliocentric system, we understand that there's 2 planes, and we look at them in a different way. I'm going to draw below it here the plane of the Earth's orbit. Okay. And that's what's shown by this red. Okay, and so here would be the sun over in here, and here would be the Earth right here. And what I want to show you is something you may remember from class when I had a piece of cardboard that showed the moon's orbit. I folded it in half and I moved it along a table. and that cardboard was inclined by 5 degrees. That's the 5-degree inclination right there. And so here's the Earth right there. And at the point at which you could have had a solar eclipse, the moon, this is the plane of moon's orbit. The point at which you could have had an eclipse, the moon, this big blob right there, was below the place where its shadow would have struck the Earth. In fact, its shadow would be along a cone that would lie out behind the moon, and it would not fall on the Earth. We'd not see an eclipse. So this funny thing I've drawn down here is a shadow. And what I'm showing here is that the plane, and it's hard in this top drawing to show the plane, but what I can do is kind of sketch on here where the fold of that cardboard would have been if this was a cardboard. And the fold was like this, and here the moon is below that. When it got over to this position over in here, moon's orbit there, there's the Earth. Again, the fold is aimed in the same direction. And at this point, here's the Earth right there in the middle. And at this point, the moon could have come smack between the Earth. Its shadow, a long cone extending out from the moon, would have fallen directly on the Earth, and we could have had an eclipse. So right now we're in the part of the year where we're in the time when we can have an eclipse occurs in January, and then about 6 months later in July. Those are called the eclipse seasons. And this view over here, which would have been, let's just say it's September, no eclipse is possible. So that's the explanation in the heliocentric system.